We now introduced as part of this section VLAN routing as a means of facilitating communication between VLAN-defined broadcast domains. The implementation of VLAN technology within an enterprise network effectively establishes broadcast domains that control the scope of traffic. One of the limitations of broadcast domains is that communication at the link layer is hindered between hosts that are not part of the same VLAN. Traditional link layer switches supporting VLANs are not capable of forwarding traffic between these broadcast domains, and therefore routing must be introduced to facilitate communication. The application of VLAN routing when using link layer switches, together with a device capable of routing VLAN traffic, is introduced, along with details of how Layer 3 switches capable of network layer operations can enable communication over VLAN-defined broadcast domains. So upon completion of this section, it is generally expected that trainees will be able to explain the purpose of VLAN routing, explain how VLAN routing is achieved for Layer 2 and Layer 3 switches, as well as configure Layer 3 routing. If we go back to the principles of a VLAN, we will recall that VLANs were developed as a means for allowing logical isolation of link layer data that allowed for Layer 2 broadcast to be effectively limited to a single VLAN. As beneficial as this is to scaling the size of broadcast domains so as to more effectively manage traffic flow, it also creates a communication barrier between end stations that are considered to be associated with different VLANs. Re-establishing this communication whilst also maintaining the logical isolation of traffic at Layer 2 relies on the implementation of VLAN routing. We are able to generate a general solution to the problems faced through the use of a router that allows the data associated with one VLAN to be routed into another VLAN domain. In order to achieve this, traffic is forwarded over a VLAN trunk link that exists between the switch and router. The router provides the internetwork communication that allows VLAN traffic to be routed and returned to the switch along the same physical trunk, but now the data is associated with the destination VLAN. In order for the VLAN routing to be established, we are required to firstly establish two VLANs on the switch by associating the port interfaces connecting to the end stations as untagged, using either the access or hybrid untagged port type. The link between the switch and the router must be configured as a trunk link, which is achieved by setting the port link type to trunk on the switch port of switch A. For the router, however, we are required to support two networks in this instance over a single physical interface. To allow this to be achieved, it is necessary to set the VLAN trunk to support two or more networks at the same time. Typically, a physical interface is only able to support a single network. However, through the use of sub-interfaces, we are able to divide the physical link into logical interfaces, with each representing a gateway for one of the supported VLANs. We can see in this example that two sub-interfaces have been created on the physical Gigabit Ethernet 0/0/1 interface, and are represented by the .1 and .2 logical sub-interface units. Each sub-interface is assigned an IP address that represents the gateway interface for the VLAN, to which traffic should be forwarded to allow it to be routed to other VLANs. The router will therefore be responsible for the routing of traffic between VLANs, and as such we can see that each host references the respective router interface address as the logical gateway address for the respective VLAN. With a general understanding of the configuration requirements for establishing VLAN routing, we can begin to configure the devices within the network to support the VLAN routing operation. We begin with the configuration of the switch, to which currently two end stations are connected in the form of host A and host B, that are to be associated respectively with VLAN 2 and VLAN 3. The first step is to create the VLANs on the switch, which is performed here using the VLAN batch command to create VLANs 2 and 3. The two port interfaces on the switch associated with the end stations should be assigned as either an access port or an untagged hybrid port. However, in this case, the port link type access command is used in the respective interface view for the two switch ports. For each of the ports, we are also required to specify the default PVID that should be used, which in this case is set to VLAN 2 for frames from host A and VLAN 3 for frames from host B. For the trunk port that runs between the switch and router, we are required to set the port link type as a trunk port, and in this case should allow at least VLANs 2 and 3. However, we use the VLAN all command here to permit all VLANs over the trunk. Now we take a look at how configuration of interface Gigabit Ethernet 0/0/1 on RTA is configured in order to support the routing of VLAN traffic between VLAN 2 and VLAN 3. The first thing that is needed is for the creation of the subinterfaces that will represent the logical interface for each VLAN. These subinterfaces are to act as gateways to the respective VLANs, and so an IP address is assigned based on the network address used for each of the VLANs created. We are unable to specify on the router that this interface is a trunk port, and so we require an alternative command to allow the VLAN traffic to be processed correctly. We do this through the .1q termination VID command that is used to remove the VLAN tag from a frame and allow the packet to be routed, as well as allow tags to be added to frames during encapsulation before it is forwarded over the trunk. Additionally, it is also necessary to configure the command ARP broadcast enable that is used to support the processing of ARP broadcasts that allow reachability to be established between VLANs. Without this command, the router will discard the initial ARP request frame received via the switch. Once the configuration for VLAN routing has been implemented on the router and the relevant configuration applied to the switch, we can attempt to use the ping application to send test packets between the hosts located within the two VLANs. In this example, we are accessing the terminal of host A and generating an ICMP packet that will be sent from the IP address of 192.168.2.1 in VLAN 2 to the destination of 192.168.3.1 of host B, this part of VLAN 3. The result, as we see, is that the generated packet, with the help of the router, is able to traverse the logical boundary of the VLAN to reach hosts located within other VLANs. If we wish to understand the benefit that is applied here, we can consider a broadcast that is generated within the 192.168.2.0 network associated with VLAN 2. The broadcast frame will only be forwarded to hosts within the same VLAN, while the router will prevent the frame from reaching other hosts in other networks, as such allowing communication between VLANs, whilst at the same time maintaining the natural broadcast domain to contain link layer broadcasts to a single VLAN. Where it is required that better performance and management of VLAN traffic be supported, it may be necessary to utilize a layer 3 switch to perform VLAN routing. For enterprise networks that contain existing layer 2 based switches, the support of a router to allow VLAN routing is usually ample. However, it involves multiple devices, and traffic flow over a trunk link represents a single point of failure, where failure of the router interface means communication between all VLANs will be lost. The layer 3 switch is considered significantly more expensive, however, but allows for much more efficient forwarding of VLAN traffic with very little delay. In this case, however, we find that VLAN interfaces are used that represent the equivalent gateway subinterfaces that are implemented on the router. As such, each VLAN is associated on the switch with a VLAN interface that is allocated an IP address that operates as the gateway for the VLAN. As with any layer 2 switch, the layer 3 switch can be configured to support VLANs, through which the same configuration steps are performed. We again begin by creating the VLANs on the switch using the VLAN batch command. For each of the interfaces that are connected to the end stations, we again set these as access ports using the port link type access command under the interface view. The last step for VLAN configuration on the layer 3 switch is to assign the PVID to the access port interfaces using the port default VLAN command, followed by the respective VLAN with which the end station is to be associated. For the configuration of VLAN routing in a layer 3 switch, however, we find a number of differences in the configuration, and that the general configuration process is somewhat more straightforward. We firstly need to create the gateway for each of the VLANs that will be supported by the layer 3 switch, and we do this by creating the VLAN interface using the interface VLAN IF command, followed by the number of the VLAN with which the interface is to be associated. For the created VLAN interface, we assign an IP address that will operate as the gateway address for the VLAN and support the routing of VLAN traffic between VLANs. So then in summary for this section, we just have a couple of questions here. The first asks, what is the purpose of the .1q termination VID command? Well, the .1q termination command, if we recall, provides the means to process received tag frames carried over the trunk link. Once they are received, the frame tag can be removed and the packet routed. For frames to be forwarded via the subinterface of the router, the command enables the frame to have the relevant VLAN tag inserted into the frame header. What is required to be configured on the switch to allow VLAN traffic to be forwarded to the configured subinterfaces? Well, the switch port must be configured as a trunk port. And as with any trunk port, the VLAN traffic must also be permitted using the port trunk allow pass command.